The water tonight is very still. Out past the continental shelf, where the seafloor drops away and the ocean becomes something else entirely. Not a surface to sail across, but a volume, a depth, a darkness measured in kilometers. The water is still. There is no wind here. No current you would feel if you were floating at the surface, looking up at a sky with no moon. Just the slow, patient weight of the ocean, pressing down on everything beneath it. You are somewhere above the Atlantic, or the Pacific. It doesn't quite matter. At this depth, at this hour, every ocean begins to feel like the same ocean. Cold, dark, old in a way that has nothing to do with calendars. Below you, the seafloor is a long way down, 3,000 meters perhaps. 4. The sediment down there is fine as flour, pale, and it has been settling for millions of years, layer by layer, century by century. Each layer thinner than a page. If you pressed your fingers into it, you would leave a print that might remain undisturbed for 10,000 years. Nothing moves quickly at the bottom of the ocean. Nothing needs to. And somewhere in that sediment, scattered across the floors of every warm and temperate sea on this planet, there are teeth, large teeth. Some of them as long as your open hand, from the base of your palm to the tip of your middle finger. Triangular, serrated along both edges, dense as stone because they have had time to become stone. Their original ivory replaced, over millions of years, by minerals seeping through the sediment. They are black now, or gray, or a deep rust red depending on where they were found and what the surrounding rock contained. They are heavy. Heavier than you expect when someone hands you one. People have been finding them on beaches for a very long time. Long before anyone understood what they were being collected. Ancient Greeks found them and believed they had fallen from the sky during lunar eclipses. They called them glossopetra, tongue stones, because of their shape. Medieval Europeans embedded them into elaborate gold jewelry, hung them from chains, believed they were serpent tongues turned to stone by a saint. They were said to detect poison. They were kept in church reliquaries alongside bone fragments and splinters of wood. No one knew they were teeth. It was not until the 17th century, when a Danish anatomist named Nicholas Steno was given the head of a large great white shark and spent weeks dissecting it, that anyone made the connection. Steno looked at the shark's teeth, then looked at the glossopetri people had been collecting for centuries, and understood they were the same thing. Or rather, that the stones had once been teeth. That the earth itself was old enough to turn one thing into another. That what looked like stone had once been alive. This was a more radical idea than it might seem now. The concept that the ground beneath your feet contained the remains of creatures that no longer existed, that life itself had a history full of endings, was not yet part of how most people understood the world. Steno was standing at the edge of a very large door, and he had only begun to push it open. The teeth he was looking at, the ones the public had named tongue stones, belonged to something far larger than any great white shark. He could see that. The proportions were the same, but the scale was different. Whatever animal had grown these teeth had been considerably larger than anything alive in the 17th century ocean. He did not know how much larger. We would not begin to understand that for another 200 years. Tonight, let those teeth rest in the sediment where most of them still are, undisturbed. The ocean pressing softly down on the silty floor, the darkness complete, the temperature just above freezing. No light reaches here. No sound from the surface penetrates this far down, or rather, Sounds travel differently in deep water, becoming something abstract, a pressure rather than a noise, a sensation rather than a signal. The teeth do not know they are being thought about. Of course they don't. They are stone. But there is something about the fact of their existence, scattered across ocean floors on opposite sides of the planet, turning slowly in river sediment, occasionally washing up on beaches where a child might find one and pick it up without knowing what they are holding. That feels like a kind of presence. A record of something that was, for a very long time, one of the largest predators this ocean has ever produced. What was it, exactly? That is a question with a long history of partial answers. Science has been assembling a picture from fragments, from teeth, from a small number of vertebrae, from the shapes of bite marks left in the bones of whale fossils. And the picture that has emerged is both more specific than people expect and more uncertain. The name most people know is Megalodon, from the Greek, great tooth. It is a reasonable name, given what we have. Teeth are mostly what we have, and the first thing worth understanding, the thing that shapes everything else about how scientists have tried to reconstruct this animal, is that teeth, even extraordinary teeth, are not a skeleton. They are a beginning. A shark's skeleton is made of cartilage, not bone. Cartilage, the same soft, flexible material that makes up the tip of your nose, the curve of your ear. It is durable enough to hold a living animal together, strong enough to absorb the forces of a life spent moving through water. But cartilage does not fossilize. Not in the way bone does. Bone is mineral dense, and when an animal dies and is buried slowly in the right kind of sediment, those minerals can be replaced, atom by atom, by other minerals from the surrounding rock. The shape is preserved. The structure remains. Bone can last hundreds of millions of years in the right conditions. Cartilage dissolves. It breaks apart. It joins the water. And so a shark, when it dies, leaves almost nothing behind. The soft tissues go first, then the cartilage, and what remains, what sinks slowly into the silt, what might eventually be found by someone who knows what they are looking at, are the teeth. A single megalodon may have produced more than 20,000 teeth over the course of its lifetime. Sharks replace their teeth continuously, row after row, cycling forward like a slow conveyor, a new tooth moving into place as the old one falls. Over decades, over a long life, this means thousands of teeth drifting down into sediment across whatever range the animal traveled. This is why megalodon teeth are not especially rare, as fossils go. They turn up on riverbeds, on ocean floors, on beaches where erosion has lifted old sediment back into reach. They have been found on every continent. They have been found in the hands of children who thought they'd picked up a dark, triangular stone. But finding the teeth is not the same as knowing the animal. What the teeth tell us is certain, and worth settling into for a moment. The largest confirmed megalodon teeth measure around 18 centimeters along the slant, that is, along the diagonal from root to tip. For comparison, the largest tooth of a great white shark reaches perhaps 8 centimeters. The megalodon tooth is not slightly larger. It is in a different category. If you held one in both hands, it would cover your palm and extend past your fingers on both sides. The serrations along the edge, which were used for cutting through flesh and bone, are themselves large enough to see from across a room. The root is wide and heavy and slightly curved, designed to anchor in a jaw that was, by any reconstruction, enormous. From the teeth, from their size, their shape, their wear patterns, scientists have worked backward. They have used the proportional relationships between tooth size and body size in living sharks, particularly in great whites, which are Megalodon's closest living relatives in some lineages of thought, to estimate what a complete Megalodon might have looked like. These estimates have changed over the decades. Early reconstructions were often based on the great white's proportions, and they produced images of an animal that looked like a great white scaled up to the size of a school bus. A familiar shape, just made enormous. Later analysis suggested the proportions were likely somewhat different. The body may have been more robust, the head larger relative to the body, the fins shaped differently. The honest answer, the one that scientists return to when pressed, is that no one has seen the complete skeleton of a megalodon. No one has measured the fin span directly. No one has seen the tail. What we have is extrapolation, careful, well-reasoned extrapolation, but extrapolation nonetheless. The length estimates cluster between 15 and 20 meters, with some outliers suggesting even larger individuals were possible. 15 meters would make it roughly as long as a semi-trailer. 20 meters would put it among the largest predators ever to have existed on this planet. The weight estimates are harder and range more widely. Somewhere between 50 and 100 metric tons is often cited, though these figures carry significant uncertainty. Even the lower end of that range is difficult to hold in mind. It is a weight that belongs to the world of large whales, not to anything we picture when we think of a predatory fish. And it was a predatory fish. Everything we know suggests it was an active hunter, not a scavenger, not a filter feeder. The teeth are designed for cutting, not for straining. The bite force estimates, derived from jaw size and musculature models, are among the highest ever calculated for any animal, living or extinct. Fossilized whale bones have been found with megalodon bite marks embedded in them, and those marks tell a particular story. They are not the marks of an animal testing or grazing. They are deep, forceful, deliberate. The whale was prey. The ocean it moved through was not this ocean, not exactly. Megalodon lived primarily during the Miocene and Pliocene epochs, a span of time running roughly from 23 million years ago to somewhere around 3.5 million years ago. The continents were in slightly different positions. The ocean currents flowed differently. Sea temperatures in many regions were warmer than they are today, and the ocean was full of large, slow prey, whales that had not yet evolved the speed and cold water adaptations that many of their modern descendants carry. It was, in some ways, a different sea, one that could sustain an animal of that size, that appetite, that range. And then, around 3.5 million years ago, something changed. The teeth in the sediment become sparse, then sparser, then they stop appearing altogether. Megalodon moved through this ocean for nearly 20 million years, and then, gradually, over what may have been hundreds of thousands of years, it was gone. The reasons for that disappearance are still debated. The world was cooling. The prey was changing. Something shifted in the balance that had held for so long. But for a moment, let the numbers simply settle. 20 million years. The whole of human history fits inside that span 10,000 times over. 20 million years is a span so large the mind cannot hold it. Not really. You can say the number, let it sit in the air, but the weight of it doesn't arrive all at once. It arrives slowly, the way cold water does, in layers pressing down. Think of it this way. The first stone tools were made roughly 3 million years ago. Megalodon had already been swimming in warm, shallow seas for 17 million years before that first edge was struck from flint. By the time the earliest members of our genus were learning to shape stone, Megalodon was already ancient, already in the long, slow process of disappearing. The creature that would become us and the creature that was already leaving, they overlapped, briefly, in time. Not in space, not in awareness of each other, but in the same turning world. And the world was turning. That is perhaps the simplest way to describe what happened in the late Pliocene, in those millions of years when the teeth in the sediment became sparse and then stopped. The planet cooled. The ice at the poles thickened and spread. Sea levels dropped. The shallow, warm seaways that had connected ocean basins began to narrow and close. The Isthmus of Panama, that thin strip of land that now separates the Atlantic from the Pacific, rose up fully from the sea around 3 million years ago, cutting off a current that had circulated warm water between the two oceans for tens of millions of years. The temperature gradients in the ocean shifted. The patterns of upwelling, of nutrient flow, of where warm water pooled and where cold water pressed in from below. All of it changed. Megalodon needed warm water. This much is reasonably well established. The teeth that have been found cluster in the warmer latitudes, in the remnants of what were once warm coastal shelves. The shark almost certainly could not regulate its own body temperature the way warm-blooded animals do, and it would have been constrained by the temperature of the water it moved through. As the cold spread, as the warm shallows contracted, the range that Megalodon could occupy would have shrunk. And the prey was changing too. The baleen whales that inhabit the colder oceans today, the humpbacks, the fins, the blues, are in some ways built for a world that Megalodon helped to shape, and then could not follow into. They are faster than their ancestors were. They are more maneuverable. And, crucially, they had begun to exploit the cold, nutrient-rich waters at higher latitudes, waters that were growing richer as the climate shifted, but waters that an animal like Megalodon could not easily follow them into. The prey was moving toward the cold. The predator was constrained by it. There is a version of this story in which the disappearance of Megalodon was not a sudden collapse, but a slow withdrawal, a pulling back from the edges of its range, a contraction. The last individuals may have persisted in shrinking pockets of warm water, in places where the old conditions held longest. Then those places cooled, or the prey moved on, or the populations simply fell below the threshold at which they could sustain themselves. Apex predators require enormous amounts of food. A very large shark, a shark of that size, would have needed to eat a great deal, and frequently enough to maintain that mass, to reproduce, to keep the population viable. When the prey becomes scarce, the margins narrow quickly. The sediment remembers none of the individuals. It only remembers the teeth. And the teeth tell us only where the animal was and when, not how the last ones died, not where the final generation lived out its last years. The fossil record is not a story with an ending. It is more like a signal that simply stops. The teeth are there, and then they are not, and the water closes over the gap the way water always does, smoothly, without a mark. What remains now is the shape of what it was, the size, the architecture of a predator so well suited to its time that it endured for nearly twice the span of the dinosaur's final chapter. It was not a failed experiment. It was a success so complete that it lasted longer than most large animals in the fossil record. It simply ran up against a world that changed faster than it could follow. And somewhere in the very deepest part of that thought, there is something worth sitting with for a moment. The ocean that Megalodon swam through is the same ocean that still exists below us now. The water is older than the shark. The dark, cold layers of the abyssal ocean were old when Megalodon was alive, and they are older still now. The shark passed through. The water remained. It continues to move in those slow, vast currents, the thermohaline circulation, the great global conveyor, the same circulation that was disrupted when the Isthmus of Panama closed, the same shifting of cold and warm that the last megalodons felt contracting around them. The water carries none of that. It is simply cold and dark, and still in its deepest places, moving in its slow geological way, as it has always moved, long before the shark and long after. And yet the teeth remain. That is the strange thing. The water carries nothing forward, no memory, no evidence, no record of what moved through it, but the teeth persist. Scattered across the seafloor in their hundreds of thousands, buried in sediment, pressed into the substrate of seamounts and continental shelves, resting in the quiet dark at depths that no light has ever reached. The shark is gone. The teeth are still here. A Megalodon tooth is not a small thing. The largest confirmed specimens measure just over 18 centimeters from root to tip, roughly the length of a human hand held open. But that measurement doesn't carry the full weight of what you're looking at when you hold one. It is the thickness that surprises people, the density, the way it feels heavier than it should, as if something of what it once was is still stored inside the enamel. Shark teeth are not bone. They are closer to the hardest parts of us, to enamel, to the material of our own teeth, compressed and mineralized over millions of years into something that resists almost everything the ocean can offer. Pressure, cold, dissolution, time. They survive all of it. And so the seafloor is a kind of archive, not of Megalodon exactly, but of its teeth. The animal shed them continuously throughout its life, the way all sharks do. A conveyor of teeth, row behind row, moving forward as each one was lost or worn down. A single Megalodon may have produced and shed as many as 40,000 teeth across its lifetime. And it lived, on average, somewhere between 20 and 40 years, though some estimates push higher. That is a long time. That is an enormous number of teeth, falling slowly through the water column, coming to rest on the seafloor, being buried, being preserved, waiting. Most of them are still there. The ones that have been found, collected by researchers, dredged from the seafloor by research vessels, turned up by divers on shallow shelves where ancient sediment lies close to the surface, represent only the smallest fraction of what exists. The ocean is very large. The sediment is very deep. There are places where Megalodon teeth have been found at the bottom of seamounts miles below the surface, in layers of sediment that date to the Miocene, 15 million years old, and beside them, in the same sediment, teeth from what appears to be much later, the Pliocene, 3 million years ago, 2.5 million. The record in the sediment is not perfectly continuous, and dating isolated teeth is imprecise, but the story the sediment tells is one of long, slow presence. And then the presence ends. There is a layer, not a sharp line. The seafloor doesn't work that way. Layers compress and mix, and what looks like a boundary is often a gradient. But there is, in multiple locations across the world, a horizon in the sediment below which Megalodon teeth appear, and above which they do not. That horizon corresponds roughly to the transition between the Pliocene and the Pleistocene, somewhere around 2.5 million years ago. The teeth stop, not everywhere at once. The record is uneven, patchy, the way all fossil records are patchy. There are suggestions that some populations persisted longer in certain regions, in warmer, deeper water, farther from the coastlines that were cooling. But the weight of the evidence, read carefully and slowly, points toward a relatively compressed period of disappearance. Not instantaneous by human standards, but fast by geological ones. Perhaps a few 100,000 years, perhaps less. What the teeth cannot tell us is what that ending felt like, from the inside. Whether it was hunger that came first, or cold, or the slow failure of reproduction as the prey grew scarce. Whether the last animals moved deeper, following warmth, or stayed in the shallows where they had always hunted and found less and less. Whether there was a last one, somewhere, in some unnamed stretch of ocean, and what the water around it looked like in those final years. We have no way of knowing. What we have are the teeth and the sediment, and the absence above a certain layer, and the understanding that absence in the fossil record is its own kind of evidence. Absence means nothing was there to leave a trace, and Megaladon, which left traces so readily, so prolifically, in so many places, in such durable form, stopped leaving them. The ocean kept moving. The sediment kept settling. New layers pressed down over the old ones, and the teeth of Megalodon were buried deeper and deeper, compressed further into the substrate, until they were simply part of the record that the seafloor keeps of everything that has ever lived and died in the water above it. Below us now, somewhere, probably many places scattered across the wide continental shelves and the flanks of seamounts in several oceans, there are teeth resting in silt that have not moved in 2.5 million years. The water above them is very cold. It moves slowly in those deep places, in the currents that carry no memory of what they once touched. The teeth are dark now, stained by the sediment around them, heavier than they were when they first fell. Patient in the way that only objects without awareness can be patient. They are simply there, waiting for nothing. In the dark, under the weight of all that water, undisturbed. And then sometimes they are found. Not often. The ocean floor is vast, and most of it will never be touched by human hands or seen by human eyes. But over the last 2 centuries, in certain places where the sediment has eroded, or where tectonic shifts have tilted ancient seabeds closer to the surface, Megalodon teeth have been pulled from the dark. Divers find them in shallow coastal waters off the Carolinas, off Florida, off the coasts of Peru and Australia and Japan. Fishermen dredge them up in nets. Collectors wade into rivers where erosion has exposed Miocene and Pliocene deposits, and they sift through gravel until they find the unmistakable triangular shape, serrated along both edges, heavy as a stone. The largest ones are longer than a human hand, 7 inches from root to tip, some longer. When you hold one, and people do hold them in museums, in private collections, in the back rooms of fossil shops, the first thing you notice is the weight. It is denser than you expect. The enamel is smooth, glassy, often stained brown or black or gray depending on the minerals in the sediment where it rested. The serrations along the edges are still sharp enough to catch your fingernail if you run it along the blade. This tooth was designed to shear through flesh, through bone, through the thick blubber of whales that no longer exist. It did that work for years, maybe decades, in the mouth of an animal that was, by every measure we have, the most powerful predator the ocean has ever produced. And now it sits in a display case, or on a shelf, or in a drawer. Silent, inert. a fragment of a creature we will never see whole. What we know about Megalodon comes almost entirely from teeth. Thousands of them collected from dozens of sites across the world. Cartilage does not fossilize well. It decays, it collapses, it leaves almost nothing behind. So we have no Megalodon skeletons, no intact jaws, no vertebrae arranged in sequence to tell us exactly how long the body was or how the spine flexed when the animal turned. We have teeth, and we have a few fossilized vertebral centra, small disc-shaped bones from the spinal column, scattered and rare. That is all. From this, we reconstruct. The teeth tell us size. By comparing Megalodon teeth to the teeth of modern great white sharks, the closest living relative we have, though the relationship is more distant than it first appears, we can estimate body length. The math is imperfect, built on assumptions about proportionality and growth rates, but it gives us a range. Most estimates place adult megalodons between 40 and 60 feet long. Some suggest they could have reached 70. There is debate. There is always debate when the evidence is incomplete, but even at the lower end of the range, we are talking about an animal 3 times the length of a large great white, and many times its mass. A predator operating at a scale the modern ocean does not support. The teeth also tell us diet. The serrations, the thickness of the enamel, the shape of the crown. All of it points to an animal built to hunt large prey. Whales, most likely. Baleen whales in particular, which were abundant during the Miocene and Pliocene, and which would have provided the caloric density an animal of that size required. We have found whale bones from that period with bite marks that match the spacing and shape of megalodon teeth. Deep gouges, sheared ribs, evidence of attacks that were not tentative or opportunistic, but deliberate and overwhelming. This was not an ambush predator. It was too large for that. It could not hide. It did not need to. It likely hunted in open water, using speed and power to close the distance, then delivering a single catastrophic bite to immobilize its prey. The bite force has been estimated, again through comparison and modeling, at somewhere between 24,000 and 40,000 pounds per square inch. Enough to crush bone. Enough to sever a whale's spine in one motion. Enough to make resistance irrelevant. And yet, for all that power, it is gone. The last megalodon teeth in the fossil record date to around 2.6 million years ago, at the boundary between the Pliocene and Pleistocene epochs. After that, nothing. No younger teeth. No evidence of survival into the ice ages. The species simply stops appearing in the geological record, and we are left to ask why. The question of why feels simple at first. A large animal disappears. Something must have killed it, or the thing it ate disappeared, or the world it lived in changed around it. These are the explanations that come easily, and all of them contain some portion of the truth. But the disappearance of Megalodon is not a simple story. It is a convergence. Several pressures arriving from different directions, none of them alone sufficient, together forming something the animal could not endure. The first pressure was the ocean itself. Around 3 million years ago, the world began to cool. Slowly, the way these things always happen, not in a single season or a single century, but across hundreds of thousands of years of gradual shift. The polar ice sheets expanded, sea levels dropped, the shallow, warm coastal seas that had dominated the planet's margins for millions of years began to contract. And this mattered enormously for Megalodon, because Megalodon did not give birth in open deep water. It gave birth in the shallows, We know this from the fossil record in a specific way. In certain coastal sites, along what was once the eastern edge of North America, in parts of Europe, along ancient shorelines that are now dry land, paleontologists have found concentrations of very large megalodon teeth alongside concentrations of very small ones. The large teeth belonged to adults. The small teeth, proportionally shaped but dramatically reduced in size, belonged to juveniles. Newborns, perhaps, or animals only a few months old. These were nurseries, places where female megalodons came to give birth, where the young could grow in water shallow enough to offer some protection, where prey was abundant, and the open ocean predators that might threaten a newborn apex predator. Other large sharks, early cetaceans, were less likely to venture. The logic of a nursery is the same whether the animal is a sea turtle or a great white or something 40 feet long with teeth the size of a human hand. When the shallow seas contracted, these nursery sites became smaller. Some disappeared entirely. The coastlines shifted. The water that had been warm and protected grew cooler or shallower still, or simply ceased to exist as habitat. And a species that requires specific coastal conditions to reproduce cannot simply move those conditions somewhere else. Drift with that for a moment. The cold settling slowly over the shallow margins of the world. The water pulling back from the land. The ancient nursery grounds going quiet. There was also the question of food. Megalodon's primary prey, the large baleen whales and other marine mammals it had evolved alongside, were themselves changing. Some species were declining. Others were migrating toward polar waters as the climate shifted, following prey of their own into colder seas. That Megalodon, adapted to warmer temperatures, may not have been able to follow comfortably or efficiently. The energy cost of moving cold water through an enormous body, of maintaining the metabolism that powered an animal of that scale, was not trivial. If the prey moved toward cold, and the predator could not follow without significant cost, the margin between survival and starvation narrows. And then there was competition. This is the part of the story that researchers have examined carefully in recent decades, because it involves an animal still with us, one you would recognize. The great white shark, Carcharodon carcharias, appears in the fossil record during the same late Miocene and Pliocene period when Megalodon was beginning its decline. The great white is smaller, considerably smaller. An exceptional great white might reach 20 feet. Megalodon was twice that. But size is not always the determining factor in who eats what. Great whites are capable of hunting in colder water. They are faster relative to their size, more maneuverable. They share a significant overlap in prey with juvenile Megalodon, the medium-sized marine mammals, the smaller cetaceans. And a juvenile Megalodon, still growing, still dependent on the nursery shallows, is not the apex predator that a 40-foot adult is. A juvenile Megalodon competes with a great white on something much closer to equal terms. If great whites were moving into the same shallow coastal waters that served as Megalodon nurseries, competing for the same prey in the same places during the most vulnerable phase of Megalodon's life cycle, the pressure on the species would have compounded everything else already working against it. Not predation, competition. The slow, invisible pressure of another animal taking a share of the same resources. The water dark and cool above you now, the seafloor somewhere far below, covered in the slow settling of sediment that has been falling for millions of years. Tiny particles of shell, of bone, of organic matter drifting down through thousands of feet of water to land without sound, without weight, accumulating in layers that record everything and forget nothing. Somewhere in those layers, the last teeth of the last megalodons are resting. We have found many of them. We have not found all of them. And the gaps between what we have found and what we have not found are where most of the questions live. Those gaps are not empty. That is the important thing to understand about them. A gap in the fossil record is not the same as an absence of life. It is an absence of preservation, which is a different thing entirely, and a distinction that changes how we read everything we think we know. Fossilization is rare. For a tooth to survive the millions of years, a specific sequence of events has to occur in a specific order. The tooth has to fall in the right place. The sediment around it has to have the right chemistry. The burial has to happen quickly enough to prevent scavenging and dissolution. And then the whole column of earth above it has to remain undisturbed for long enough that the tooth survives into a time when someone is walking along a creek bed or diving along a shallow shelf and happens to look in exactly the right direction. Most teeth never make it. Most animals leave nothing behind. The sea is very good at consuming what enters it. So, when we look at the Megalodon fossil record and see a thinning, fewer teeth, spread across fewer locations, concentrated in certain basins and absent from others, we are not necessarily seeing the full picture of where Megalodon was, or how many remained, or how quickly the population declined. We are seeing the picture that the sediment chose to preserve for us. That picture is incomplete in ways we cannot fully measure. What we can say is this: the youngest Megalodon teeth, the ones dated most reliably to the end of the species, cluster around a period roughly 3.5 million years ago. Some estimates push that boundary slightly. A small number of specimens have generated significant debate about whether they might be younger still. But the broad consensus holds. By approximately 3.5 million years ago, the teeth stop. The record goes quiet. And nothing in the water since then has been large enough, or has left behind the right kind of evidence to suggest otherwise. The ocean continues slowly above this. There is a moment, and it comes to almost everyone who spends time thinking about Megalodon, when the sheer scale of the animal stops being a fact and becomes something closer to a sensation. Not excitement, something quieter than that, a kind of vertigo that comes from trying to hold two things in mind at the same time: that something so large existed, and that it is gone. 18 meters. Perhaps more, moving through water that looked, from the surface, exactly like the water we have now. The same blue-gray color in the shallows, the same black in the deep, the same surface catching light in the morning and releasing it again at dusk, the same cold rising from below in certain latitudes, the same slow circulation of warm and cold water around the curve of the earth. The ocean did not look different when Megalodon was in it. That is the part that settles in slowly. There was no signal from the surface. No way to tell, looking down from above, that somewhere in the middle column of water, not at the surface, not at the bottom, but somewhere in between, where the light begins to fail, something the length of a city bus was moving through the dark. It did not need to be seen. It had no need of that. And the water above you now is the same water. Older, in the sense that it has moved through more cycles, more evaporation and rain and runoff and current, but chemically, structurally, in the way it behaves and sounds and feels, the same. The same pressure at depth. The same coldness arriving from the poles and sinking, turning, moving slowly along the bottom toward the equator, and back again over the course of centuries. Megalodon moved through the ancestor of this water. The teeth it shed drifted down through that water and landed in sediment that has since compressed and shifted and been covered over by millions of years of additional settling. Some of that sediment is at the bottom of trenches no one has fully mapped. There is always more to say about the ocean floor, and almost none of it has been said yet. Less than a quarter of it has been surveyed with the resolution that would allow us to see something the size of a tooth. The rest is a shape without detail, contours on a map, depths recorded, but surfaces unseen. This is not a source of mystery in the dramatic sense. It is simply the condition of the ocean. It is very large and very dark, and it has been here for a very long time. The Megalodon teeth we have found are enough to tell us the shape of the animal, the arc of its range, something about how it fed and where it birthed its young. They are enough to tell us approximately when it disappeared. What they cannot tell us, what no amount of additional teeth will ever fully answer, is what it was like to be inside that disappearance. Whether it happened slowly enough that no individual animal experienced it as an ending. Whether the last ones lived in diminishing groups or entirely alone, following prey that was itself becoming harder to find. That is the kind of question the sediment cannot answer. The sediment records presence. It does not record awareness. But the water carries something. Not memory, water has no memory. But the water at depth has a quality of stillness that makes it easier to hold these questions without needing them resolved. The cold down there is very complete. And that completeness, that quality of cold and stillness, is perhaps the closest we can come to imagining what the deep ocean held, long after the Megalodon was gone from it. Not an absence exactly. More like a room where something very large once stood, and the air has simply adjusted around that missing shape over millions of years, until the room no longer remembers what it was organizing itself around. The ocean forgets. That is one of its properties. But we have other tools beyond the teeth, and they tell a quieter story than the teeth do, but in some ways a more complete one. One of those tools is comparison. Living animals, specifically the great white shark, which is not a descendant of the Megalodon, despite what is sometimes said. The two lineages diverged far earlier than that. But the great white is, in some functional sense, the closest thing the modern ocean has to an analog. A large, warm-blooded, prey-hunting, open-water predator with a cartilaginous skeleton and a jaw that accounts for much of its strike force. Studying the great white, how it moves, how it hunts, how deep it tends to go, how much it needs to eat, gives us something to scale from. A kind of proportional reasoning. The great white can reach 6 meters, possibly slightly more in the largest confirmed individuals. The Megalodon was, by most serious estimates, somewhere between 15 and 20 meters for mature adults. Some estimates push higher, but the more careful reconstructions tend to settle in that range. That is not simply a larger version of the same animal. At that scale, the physics of movement through water change. The energetic demands change. The relationship between surface area and volume shifts in ways that affect thermoregulation, which affects hunting range, which affects how large a territory an individual would have needed. These are not small differences. They are differences in kind, not just degree. A 20-meter shark maintaining the kind of active predation we associate with the great white would have needed an extraordinary amount of food. The estimates vary, but researchers working from metabolic scaling laws, the same kind of math used to understand how dinosaurs fed, how whales manage long migrations, suggest that a mature megalodon would have needed to consume something like 1,000 kilograms of food per week. Perhaps more. That is not a guess. It is a reasoned inference from bodies of work in metabolic ecology that have been tested against living animals and found to hold. What that means, practically, is that the megalodon was not a solitary patient ambush predator in the way some smaller sharks are. It needed large prey, reliably available in waters it could reach. For most of its existence, across roughly 20 million years, that prey existed. The Miocene and Pliocene oceans were full of large marine mammals. Whales were diversifying rapidly. There were species we have no common name for, giant relatives of today's baleen whales, slower moving and more abundant in warm, nutrient-rich coastal zones. Sirenians, the manatee relatives, were widespread across tropical and subtropical seas. The prey base was rich, and it matched what the megalodon needed. Then, slowly, things changed. The cooling of the oceans is part of the story, but only part. The other part is the prey itself. As the climate shifted and the warm coastal seas that Megalodon relied on began to contract, the whale lineages that had been feeding in those zones were under pressure. Some went extinct. Others shifted toward colder, deeper, more polar waters, following the krill, following the nutrient upwellings that were themselves moving with the changing currents. The prey was not simply gone. It was moving into places that may have been energetically costly for the megalodon to follow. Whether it tried to follow is something the fossil record cannot say clearly. What it records is that megalodon teeth appear in warm water formations and then stop appearing in those formations. They are not replaced by teeth in cold water formations in the same abundance. The animal does not seem to have made the transition. Whether that is because it could not, physiologically, thermally, energetically, or because it did not, we do not know. There is something in that uncertainty worth sitting with. The idea that a creature that had persisted for 20 million years, through other periods of climatic stress, may have been held back by something as particular as water temperature. The difference between 13 degrees and 9 degrees Celsius, a margin that, to us, is almost imperceptible. But to an animal whose hunting performance, whose digestion, whose ability to process and convert prey into movement and heat was tuned over millions of years to a specific thermal band, that 4-degree shift may have been a wall. The ocean is full of walls like that. Invisible ones, lines of temperature and salinity and pressure that are as real to the animals living within them as any physical barrier. Creatures don't cross those lines simply because they need to. They are shaped by them over so much time that the line becomes part of what they are. The megalodon was shaped by warmth, by the rich, slow, warm water margins of a world that no longer exists in quite that form. And somewhere in that slow revision of the world's oceans, in that centuries-long cooling, that gradual retreat of the conditions it had always known, the last individuals swam through water that was getting harder to read, prey that was moving in patterns that no longer matched what their bodies had been built to expect. The cold is still here. The dark is still here. And something else was happening during those final millennia. Something slower than temperature, and harder to name. The Megalodon had spent most of its existence in a world with a particular kind of abundance. The shallow inland seas, the warm coastal margins, the slow-moving prey that had evolved alongside it over millions of years, all of that had created a specific kind of hunter. One shaped not for versatility, but for depth of mastery. It knew one thing with extraordinary precision. It knew how to do what it had always done, in the conditions that had always held. And that is not a flaw. That is what survival looks like, across geological time. You don't become the largest predatory fish that ever lived by being flexible. You become it by being exactly what you are, completely with nothing left over. Every kilogram of that body, every degree of that jaw's arc, every calorie burned in a slow, efficient pass through warm water. All of it shaped by 30 million years of refinement. The Megalodon was not a rough draft. It was something very close to finished, which is part of what made the ending so quiet. There was no catastrophe sharp enough to name, no single winter, no single year when the last one died. The cooling of the oceans was measured in centuries. The retreat of the shallow seas, the reorganization of the current systems that had kept the warm margins warm. All of that moved at a pace that a human life could never have detected. You could have lived your entire life on the edge of that world, fishing its waters, watching its surface, and seen nothing change. But the Megalodon's prey was changing. The baleen whales, which had become a central part of its diet as other prey thinned, were evolving too. They were becoming faster, more migratory, moving through colder water, following the cold current blooms of krill and small fish into latitudes that the Megalodon's body was not built to follow. The prey was not disappearing. It was relocating into water that was a few degrees too cold, a few 100 meters too deep, just a little further from the margins where the Megalodon had always hunted. Somewhere in the dark water below us, that gap between predator and prey was widening. Slowly, the way a tide goes out, not all at once but in a long, indifferent withdrawal. And the teeth fell. That is what the fossil record is made of, mostly. Teeth. Thousands of them, pulled from coastal sediments, from the beds of rivers that used to be seafloors, from the slow accumulation of ocean floor sediment that took millions of years to form. Each tooth a moment, each one a single feeding, or a lost replacement, or the slow settling of a body into silt long after the last breath. The youngest Megalodon teeth that have been reliably dated cluster around 3.5 million years ago. Some estimates reach a little further, toward 3 million. The margin of uncertainty is wide enough that you could fit several human civilizations inside it. But the clustering is real. The teeth become rare, then rarer. Then, in the layers that correspond to the world as it is now, nothing. The ocean kept going. The whales kept going. The smaller sharks kept going, filling the spaces the Megalodon had occupied, doing so in their own way, with their own constraints. The great white shark is sometimes mentioned here, as though it inherited something. And in a loose ecological sense, it moved into some of the same territories. But the great white is not a descendant of the Megalodon. It belongs to a different lineage, arrived at through a different path. The resemblance is convergence, two very different animals arriving at a similar shape because the shape works, because the ocean produces the same solutions, independently across time. The Megalodon's actual lineage, the otodontids, the broad-toothed warm-water sharks that had dominated for tens of millions of years, ended with it. There are no living relatives close enough to carry the line forward in any meaningful sense. The branch simply closed, and the ocean is still here. That is the thing that stays with you, if you sit with it long enough. The water that the Megalodon moved through is still here, rearranged, cooled, redistributed across different currents, but the same water. The calcium in those teeth came from ancient seas, cycled through bodies and sediment and rock and rain and sea again, probably many times over. Nothing is really lost in that sense. It is all still moving. It has just changed form. The deep parts of the ocean, where the pressure builds slowly and the light has never reached, were there before the Megalodon. They will be there long after the last trace of it dissolves from the sediment. That dark, that cold, that weight of water pressing down from miles above, none of it noticed the Megalodon's absence. The ocean does not mourn. It does not mark. It simply continues. Down here, in the low, cold dark, something is still moving. Something is always moving down here. That is the first thing to understand about the deep ocean. It is not still. It never has been. The currents that run along the seafloor are slow, sometimes barely measurable, but they are persistent. They have been moving in the same general directions for millions of years. The Megalodon lived inside those currents. It was shaped by them. Its body understood the pressure differentials, the temperature gradients, the way prey would orient itself against the flow, and those currents are still moving now in the same slow directions, carrying whatever the water carries. Silt, dissolved minerals, the microscopic remains of things that once lived and sank. There is something worth sitting with in that. The water is not a backdrop. It is not empty space through which animals move. It is a medium with its own history, its own memory of a kind. Not conscious memory, but the kind that is written in temperature and salinity and the slow orbital chemistry of deep circulation. When we talk about what we know of the Megalodon, we are also talking about the ocean it lived in. And that ocean is not entirely gone. It has rearranged itself. It has cooled in some places, warmed in others. The currents have shifted their courses across geological time. But the deep basins, the wide cold floors, the pressure at 4,000 meters, those have been more or less constant for a very long time. The Megalodon knew a version of this dark, a warmer version in some eras, a version with different coastlines above it, but this dark. What the fossil record gives us, in the end, is an outline, the shape of teeth, occasionally the texture of a vertebral disc. From those pieces, scientists have inferred a great deal, and inferred carefully, which matters. The estimates of body length have changed over the decades as our methods have improved. Early reconstructions, often based on scaling up the white shark, produced numbers that were probably too large. More recent work, using different reference points and accounting for the proportional differences between species, has brought those numbers down somewhat. Not dramatically. The Megalodon was still one of the largest predatory animals that has ever lived. But the process of revision is important. It is science doing what it is supposed to do. Looking again, measuring differently, admitting that the earlier model was incomplete. That process is still ongoing. There are researchers working right now in universities and natural history museums with collections of teeth that have never been fully analyzed. Some teeth have been scanned with equipment that did not exist 20 years ago. The internal structure of the tooth, the density of the enamel, the geometry of the root, contains information that the tooth's outer surface does not reveal. The same is true of the few vertebral centra that have been recovered. Bone, or what functions as bone in a shark, holds a record of growth, of stress, of diet in certain chemical traces. That record is being read, slowly, carefully, by people whose names most of us will never know, working in rooms that do not feel like the ocean at all. But the ocean is where the answers came from, and the ocean is where they will eventually return in one form or another. That is not a poetic observation. It is simply the way of things in a world where calcium cycles through systems that are older than any individual animal, older than any species, older than the configuration of continents we currently live on. The Megalodon's reign, if you want to call it that, lasted somewhere in the range of 13 to 15 million years. That is a difficult number to hold. Humans, in any form that would be recognizable as human, have existed for perhaps 300,000 years. The entire span of recorded history, writing, agriculture, cities, is perhaps 10,000 years. The Megalodon was swimming and hunting and growing and dying for a period roughly 50 times longer than humans have existed in any form. And then it ended. The ending took time, probably. Not a single event, not a single year. A slow contraction of range, a thinning of population, a gradual narrowing of the viable world until there was no viable world left. We do not know exactly what it felt like, from the inside of that species, to be ending. That is not a question science can answer. But we can look at other large predators that have declined and observe the pattern. Range contracts toward the equator, or toward refugia, where conditions remain suitable a little longer. Prey becomes harder to find. Juveniles, who need shallower, warmer water, find less of it. The population ages, in a sense. Fewer young survive to replace the adults. And eventually the last individuals, wherever they were, swam through water that none of their kind had swum through before. Water that was, for them, the edge of a world that was closing. That image stays with you. Or it stays with me. The last one, wherever it was. Moving through cold water, finding nothing again. The ocean around it unchanged, indifferent, full of its own slow business. And then not moving. The teeth sank. They settled into sediment. They began the long, slow process of becoming part of the seafloor, and the ocean continued, the way it always continues, in its cold, dark, patient way, not noticing, not marking, simply moving. There is something in that image that is difficult to leave behind. The teeth settling, the slow accumulation of silt over something that had, for millions of years, been the largest predatory presence in the ocean. There is a particular kind of quiet that comes after the end of a thing, and the seafloor holds it well, better than anywhere else. The seafloor has been holding the ends of things for a very long time. But here is what we know, and what we do not know, and where the line between them sits. We know the teeth. That is, in some important sense, where almost all of our knowledge comes from. Megalodon left behind its teeth the way a fire leaves behind ash, in quantity, in layers, across enormous distances. Teeth have been found on the floors of the Pacific and the Atlantic. They have been found off the coasts of every inhabited continent. They have been found in sediment that is 15 million years old, and in sediment that is 3 million years old. Some collectors have pulled them from riverbeds where ancient seafloors have been lifted and eroded over time. Some have been found still resting where they fell, on the abyssal plain, dark and heavy and intact. The largest confirmed specimens measure around 18 centimeters from root to tip. That is roughly the length of an adult human hand. The teeth tell us shape and size and, in broad terms, age. They tell us that Megalodon was a lamniform shark, related more distantly than some once thought to the modern great white. They tell us that the serrations along the edge of each tooth were fine and numerous, designed for slicing through bone as much as flesh. A great white's teeth cut and tear. Megalodon's teeth, at that scale, could shear through the rib cage of a large whale. The teeth are the evidence. The teeth are almost everything. What we do not have is a spine. Shark skeletons are cartilage, not bone, and cartilage dissolves. It leaves almost nothing in the fossil record. We have, from Megalodon, a handful of calcified vertebrae, dense enough to fossilize, and that is nearly the extent of the skeletal record. One partial vertebral column was found in Belgium in the 19th century. A few isolated centra have surfaced since. That is roughly the whole of it. For a creature that may have reached 15 or 16 meters in length, possibly more, the physical remains amount to a small collection of teeth and a few discs of calcified cartilage. Everything else, the shape of the body, the arrangement of the fins, the exact proportion of the head, is inference. And inference is not nothing. Inference built on good data, on careful comparison, on an understanding of how closely related species are structured, is how science fills in the gaps that preservation cannot. But it is worth sitting with the fact that the body of Megalodon has never been seen. No one has looked at its outline. No one has measured its girth. The reconstructions that exist, the open-jawed models in museum halls, the illustrations in books, the silhouettes on screens, are all built from extrapolation. The teeth anchor the model. Everything else is reasoned outward from them. This is not a criticism. It is simply where the evidence ends and the careful work of reconstruction begins. Scientists who study Megalodon are working at the frontier of what fossilization makes possible, and they are honest about that frontier. The uncertainty is part of the science. The uncertainty is, in its way, part of the story. What we can say with some confidence is this: Megalodon was almost certainly a warm-water coastal shelf predator for much of its existence, with a preference for the productive zones where large marine mammals concentrated. It had a global distribution because the warm coastal environments it favored were, during the Miocene, globally distributed. It was likely warm-blooded in the regional sense, as modern great whites are, able to elevate body temperature above the surrounding water by retaining heat from muscular activity. This would have made it faster, more metabolically active, more effective in cooler water than a purely ectothermic shark of the same size could be. But it still needed warmth, still needed prey, still needed the particular conditions that its size and its biology demanded. And then those conditions narrowed. And the creature narrowed with them, in the sense that populations contracted and fragmented. And then the populations were gone. The teeth remain. Scattered across the floors of oceans, the shark no longer swims, resting in sediment that has continued to accumulate, slowly, grain by grain, over the millions of years since. The ocean is patient with its dead. It covers them gently and keeps them cold, and does not disturb them more than the slow settling of time requires. There are places in the Pacific where Megalodon teeth have been found crusted with manganese nodules. The slow mineral accretion that deep-sea objects gather over millions of years. The rate of manganese accumulation is known. It is slow, extraordinarily slow. And the crust on some of these teeth suggested ages of many millions of years, which aligned with what the sediment record already indicated. The teeth were old in the way the seafloor is old, patient, accumulated, belonging now entirely to the past. And yet the water above them moves. The ocean above them continues. The same cold, patient dark that received those teeth continues, unhurried, unaware. And there is something in that continuity worth sitting with for a moment. The ocean does not register absence. It does not record what is no longer swimming through it. The water that now fills the spaces where Megalodon once moved is the same water, chemically, physically, in its cold, dark weight as it was then. Oceans do not mourn. They do not reorganize themselves around a loss. Whatever shaped those teeth, whatever pulled them through 30 million years of open sea, is gone. And the sea continued as if nothing of consequence had changed, which, in a sense, is true. The Megalodon was enormous. It was, by any measure we have, one of the largest predatory animals that has ever existed on this planet. And yet the ocean swallowed its disappearance without a visible scar. That is perhaps the most honest thing we know about this animal. Not the length estimates, not the jaw reconstructions, not the force calculations, but this, that it lived and then did not, and the sea moved on. We have been trying, in various ways, to reverse that process, to pull the animal back out of the dark using the only evidence it left behind. And the evidence is strange in the way all deep time evidence is strange, rich in some places, absent in others, shaped by the particular accidents of what sank, what settled, what mineralized, what happened to end up in a riverbank or a dredge hall or a collector's box. We have millions of teeth. We have almost nothing else. The vertebrae help a little. There are specimens, partial vertebral columns mostly, that give researchers something to work with beyond the teeth. Shark vertebrae are made of cartilage that has been calcified, hardened enough to sometimes survive burial and time. They are still far rarer than teeth. But where they have been found and studied, they confirm what the teeth already implied: a very large animal with the proportions of a shark scaled upward, with a body that was genuinely, incomprehensibly massive. One partial vertebral column found in Belgium was studied in detail. The individual vertebrae were large enough that their size alone confirmed a shark of extraordinary dimensions. Not a shark the size of a large great white. A shark in a different category of size entirely. And yet even here, even with vertebrae in hand, the reconstruction remains incomplete. Shark cartilage does not preserve the soft tissues around it. The musculature, the organ placement, the coloration, the behavior, all of that is interpretation, inference, extrapolation from living relatives, and from the physics of what such a body would require to function. What would it have needed? A body that size, moving through cold water. It would have needed to eat constantly, or nearly so. Large, warm-blooded predators, and there is some evidence that Megalodon may have been at least partially warm-blooded, as great whites are, capable of maintaining a body temperature somewhat above the surrounding water. Burn through energy at rates that require regular, substantial feeding. The whale populations that existed during Megalodon's peak years were not the same whale populations we have today. They were different species, different sizes, different distributions. Some were smaller, some were faster, some were very large. The relationship between Megalodon and the whales it hunted was not simple. It was an ecology, a balance that had developed over millions of years, shifting as both predator and prey evolved. There is evidence, in some whale fossils, of large bite marks. Marks consistent with a very large shark. Marks on bones, which means the flesh was already gone, or that the biting was severe enough to reach bone directly. Paleontologists have looked at these marks carefully. They have compared them to what we know about how great whites attack prey, where on the body, in what direction, with what force. And some of those old whale bones carry the ghost of something enormous. Not proof of Megalodon specifically. Other large sharks existed. The fossil record contains multiple species of large shark across the same time periods, and distinguishing which left which marks requires a precision the evidence rarely allows. But the scale of some of those marks. The scale suggests something very large indeed. You are somewhere in the middle of all of this, in a sense, between the teeth on the seafloor and the bones with their ancient marks, between what is known and what can only be estimated. The animal exists, in our current understanding, as a kind of informed outline. We can draw it. We have drawn it many times in museums and textbooks and documentary reconstructions. A massive shark, gray-blue or darker, proportioned like a great white but scaled beyond anything alive today, moving through water that was somewhat warmer than what covers most of the deep ocean now. But the drawing is always an interpretation. The animal behind it remains where it has always been, in the sediment, in the teeth, in the slow, cold patience of deep time. The water settles around the thought, the way it always does out here, dark and still, and very deep. And yet there is something else worth sitting with for a moment, something that comes up quietly in almost every serious discussion of this animal. Not what we know, but what we keep wanting to believe. The Megalodon has been extinct for somewhere around 3.5 million years. That is the current scientific consensus, supported by the fossil record and by the distribution of its teeth across oceanic sediment layers. The most recent confirmed teeth date to roughly that boundary. After that point, they stop appearing. The sediment continues, the record continues, but the teeth are gone. And still the question returns. Every few years, in a documentary or a headline or a conversation on the deck of a research vessel late at night, someone asks it, could one still be out there? Somewhere deep enough, somewhere cold enough and dark enough and far enough from anything we have mapped carefully. It is worth answering this question honestly, because it keeps coming back, and because the honest answer is more interesting than either a dismissal or an encouragement. The ocean is large. That part is true. The deep ocean in particular remains incompletely surveyed. There are trenches and abyssal plains where human instruments have spent very little time. The Hadal Zone, the deepest regions below 6,000 meters, is known in fragments. If something lived there, truly lived there year after year in the dark, we would not necessarily know about it. That much is fair to say. But here is what complicates it. The Megalodon, as best we can reconstruct it, was not a deep-sea animal. It was a coastal and open-water predator operating in the warm, shallow to mid-depth zones of ancient oceans. Its diet, as far as we can tell from the fossil evidence, was centered on large marine mammals. Early whales, mostly, the kinds that gathered in warm, productive, relatively shallow water near continental shelves. The animal was built for pursuit in open, lit water, not for the cold, pressurized dark of the deep trenches. For it to have survived into the present, it would have had to change. Radically and completely. It would have needed to shift its prey base away from the warm water mammals that defined its diet, and toward something found in total darkness at crushing pressure. It would have needed to shrink, perhaps, to manage the cold, or adapt in ways we cannot fully imagine. It would have needed to do all of this without leaving any modern evidence. No bodies, no kills, no contemporary teeth washing up on beaches, no sonar returns, no sightings that have held up to examination. 3.5 million years is a long time to leave no trace at all. The water drifts. The thought settles slowly. What is more likely, and this is the part that takes a moment to absorb, is that the Megalodon's disappearance was quiet rather than sudden. Not a catastrophe. Not a single moment. More of a slow recession, like a tide going out over centuries rather than hours. The prey shifted. The ocean cooled at the edges. The competition, in the form of smaller, faster, more adaptable predators, pressed in from every direction. And the largest predator the ocean had ever produced simply could not sustain itself. One generation slightly smaller than the last. One breeding season with fewer survivors. Fewer and fewer, over thousands of years, until the gaps between individuals were too wide to close. That is the quietest kind of ending. The kind where there is no final moment, no last animal, no event to point to. Just a slow thinning. A species becoming rare, and then rarer, and then the absence where it used to be. The teeth on the seafloor are what remain of that presence. Some of them are lying in sediment that has not been disturbed since they fell, resting in complete dark under kilometers of water, surrounded by the same slow cold that has defined the deep ocean for millions of years. They are not waiting. They are simply there, the way old things are simply there, without urgency, without motion, without any sense that time is passing. When a research team recovers one, and teams still do in trawls and dredges and the occasional targeted dive, what they hold in their hands is something that was already ancient when the first humans were walking. The animal that produced it has been gone longer than our species has existed, longer than our genus has existed. The gap between then and now is not historical. It is geological. And still the tooth is smooth, still heavy in the hand, still shaped like something that worked, that functioned, that bit and held and released in water that no longer exists above shores that have long since changed their shape. There is something in that which resists easy description. Not grief, exactly. Not wonder in the excited sense. Something quieter than both. A recognition, perhaps, that the ocean holds time differently than land does. That things are preserved here, slowly, in cold and pressure and dark, in ways that keep returning the distant past to the surface. The water is very dark tonight, very still at this depth. Far above, if you were to rise slowly through the column, you would pass through cold layers and then slightly warmer ones, through zones of faint bioluminescence, and then finally into whatever light the surface holds. But down here, none of that registers. Down here, it is simply dark and quiet and old. The seafloor extends in every direction, and somewhere in that sediment, distributed across the margins of ancient coastlines that no longer exist, the teeth are resting where they fell. Those teeth have been accumulating for a long time. Millions of years of a single lineage, shedding and replacing, the way all sharks do. Thousands of teeth across a single lifetime. Tens of thousands across the full span of a species. And the species lasted roughly 13 million years. That number is worth sitting with for a moment. 13 million years. The entire history of our own genus, from the earliest Homo all the way to this present night, accounts for somewhere between 2 and 3 million years. Megalodon existed for more than 4 times that span. It was not a brief experiment. It was not a creature that appeared and quickly failed. It was one of the most enduring large predators this ocean has ever produced. And then it was gone. The question of why it disappeared is one that paleontologists have turned over carefully for decades, and there is still no single clean answer. What there is, instead, is a convergence of pressures, each one alone perhaps manageable, but arriving together in the same narrow window of geological time in a way that left very little room. The cooling comes first. Around 3.5 million years ago, the climate began a long shift. Temperatures dropped. Ice advanced at the poles. The shallow, warm coastal seas where Megalodon appears to have done much of its hunting and nursing, its young began to contract. Coastlines changed. The prey communities that had structured themselves in those warm shallows began shifting too, some species moving poleward, some declining, the whole system reorganizing around a colder and less stable ocean. And at roughly the same time, something else was changing in those colder waters. New predators were moving in. The great white shark as it exists today had been present for some time, but the lineage was diversifying and expanding its range, pushing into zones that Megalodon may have relied on. Orcas, too, were becoming more sophisticated, more coordinated, better organized as hunters. Neither of these alone could have displaced a creature as large as Megalodon, but they didn't need to displace it directly. They only needed to compete for the same prey, in the same places at the same time. For a predator that required extraordinary caloric intake simply to maintain its body temperature and mass, even modest pressure on prey availability could tip the balance in ways that smaller, more efficient hunters would not feel as severely. There is a concept in ecology sometimes called the energetic ceiling. A body of a certain size requires a floor of prey density below which it simply cannot be maintained. The animal does not starve dramatically. It does not fail in some visible way. It simply stops reproducing successfully. Fewer young survive. The population thins slowly over generations until the gaps between individuals are too wide, and the breeding networks collapse quietly, and one day the animals that remain are simply not enough to sustain the species forward in time. This is thought to be closer to how Megalodon ended than any single catastrophic event. A slow thinning. A long silence widening between encounters that eventually never close again. What is harder to recover from than extinction, in some ways, is the ambiguity around it. Because we have no complete Megalodon. We have teeth, and we have occasional vertebrae preserved in calcified cartilage, and we have the shape of an absence. Everything else is inference, careful reconstruction from what related species show us, from the physics of large bodies in water, from the distribution of those teeth across the sea floor. The creature itself has to be imagined from its edges, and so some questions remain genuinely open, and probably will for as long as our only archive is what the sediment has chosen to keep. We do not know precisely how Megalodon looked. The reconstructions that have become familiar, the wide-bodied, blunt-snouted animal rendered in museum models and scientific illustrations, are built on the teeth and on extrapolation from the white shark, which belongs to a different family. Some researchers have argued the proportions would have been different, the head broader relative to the body, the profile less streamlined, more massive in the anterior. We may be imagining it wrong in subtle ways we cannot yet detect because the evidence to correct us has not been found and may never be. We do not know its exact thermal biology with certainty, though the evidence suggests some degree of regional endothermy, the ability to maintain parts of the body warmer than the surrounding water, similar to what white sharks and tunas do today. A creature that size generating heat internally would have been an extraordinary metabolic engine. It would have required an ocean generous enough to fuel it. And we do not know, with the precision some would wish for, exactly when the last one died. The youngest teeth that have been reliably dated cluster around 3.5 million years ago. But dating isolated teeth is technically difficult, and there is always the possibility that some teeth assigned to that period belong to slightly different points in time. The margin of uncertainty is not enormous, but it is present. The last Megalodon did not leave a record of itself. It simply stopped leaving teeth. That is perhaps the most honest thing that can be said about what we know. The evidence is real, it is extensive, and it tells a coherent story about an animal of almost incomprehensible scale that shaped this ocean for longer than our entire lineage has existed. But the evidence has edges, and beyond those edges is dark water, and what is in that water we cannot say with certainty. The sediment on the seafloor shifts slowly over very long time scales. Teeth migrate upward and downward through layers, moved by pressure, by small currents, by the burrowing of organisms that still live in that cold silt. The archive is real but imperfect. The record is there, and it continues. And what remains when the archive closes is not silence. It is something quieter than silence. It is the ordinary dark of the deep ocean, the same dark that existed before the first Megalodon tooth fell to the seafloor, and the same dark that exists tonight, right now, somewhere far below you. The water does not mark what it has lost. It continues. It moves in the same slow patterns it has always moved, the cold, deep currents pressing against the warmer layers above, the pressure building with every meter of depth until the numbers stop meaning very much, and the ocean simply becomes what it has always been, immense, indifferent, and older than almost anything we know how to name. The Megalodon existed in that water for somewhere close to 20 million years. That number is difficult to hold. Our own genus has been here for perhaps 2 million. The animal that preceded everything we think of as human history, that preceded cities and language and fire and the first carved stone, was still millions of years in the future when Megalodon was already an ancient thing, already perfected, already at the center of an ocean that was not so different from this one. It fed, it moved, it left teeth. That is the record, and the record, imperfect as it is enough to say with confidence that this animal was real, that it was here, and that the ocean was shaped around its presence in ways we are still only beginning to understand. The ecosystems it occupied were different from what we see today, but not entirely different. Whales existed, seals existed, the cold and the depth and the pressure existed. The food chains that Megalodon sat at the top of were elaborate, interconnected, functioning. And then, at the close of the Pliocene, something shifted. The exact cause remains a matter of careful, ongoing debate among the people who have devoted their working lives to these questions. Cooling waters, prey migration, competition, perhaps some combination that no single paper has yet captured in full. The Megalodon's range contracted. The teeth grew scarcer in the record, and then there were no more teeth. That is extinction. Not a moment, not an event in the dramatic sense, but a slow withdrawal, a thinning. A silence that settled over millions of years rather than all at once. The last individuals of any species rarely know they are the last. They are simply animals, doing what animals do, in an ocean that is no longer quite the right shape for them. The ocean moves on. The sediment covers what they leave behind. What we are left with is a very long row of teeth in museum drawers and research collections, and from those teeth, a picture that is genuinely extraordinary. A shark that may have reached 17 or 18 meters. a bite force that exceeded anything in the modern world by a considerable margin, a distribution that once covered most of the planet's warm and temperate seas, a span of existence that dwarfs every human civilization ever built, every war ever fought, every dynasty ever named, by an order of magnitude so large it stops feeling like a comparison. And the question that surfaces eventually in nearly every conversation about this animal, the question that has followed Megalodon into popular culture and never quite let go, is whether it might still be here. Whether something that large, in an ocean that deep, could have persisted past the point the teeth stop appearing. The honest answer is no, and the honesty of that answer is worth sitting with, because it comes not from certainty in the negative sense, but from what the ocean actually tells us. Megalodon, if it existed today, would not be invisible. It would eat. What it ate would show marks. The whale populations of the modern ocean would carry those marks, and we would see them, and we do not. The coastal records would reflect its presence, and they do not. The deep ocean is large, but it is not a place where something that size could feed without trace. We have listened for those traces carefully. They are not there. What persists is the question itself, and perhaps that is its own kind of answer. Not about the shark, but about us. About the part of the human mind that looks at dark water and wants something enormous to be inside it. That impulse is not irrational. It is very old. It predates science. It predates boats. It is the same impulse that produced the sea monsters on the edges of old maps, and it is not wrong to feel it, only wrong to mistake it for evidence. The ocean at this depth right now holds things we have not named. Not Megalodon, but real creatures, genuinely strange, going about their lives in cold water under pressures we can only model. They do not need to be Megalodon to be extraordinary. The seafloor is covered in organisms we have no words for yet, feeding on chemistry instead of light, existing in temperatures close to freezing, alive in ways that still surprise the people who study them most carefully. And somewhere in all of that dark water, there is a tooth, just resting in silt, waiting in the sediment the way all of that evidence waits, patiently, without urgency, as the ocean moves slowly above it. The record continues. The water is very deep tonight. The dark is ordinary. Let yourself settle into it.